Hey guys, thank you so much for joining this session. I'm Saranyan. Previously, I was with Petuum. I was leading engineering. Petuum is an AI startup where we built models to deploy in factories around the world to autonomously run the operations of the equipments. So a lot of real world learning based stuff. So I'll be while I'm not with Petuum, right now, but I'll be sharing the lessons learned there, so that you guys have takeaway from a real work that we did, something that's really challenging. And if you have any questions, feel free to I think the protocol here is to post in the chat, and we'll pick it up. But if there are any audio-visual issues, with anything with the audio or slides not showing up right, just let me know, and we can adjust accordingly. Awesome. I'm going to cut the video just for this brief bit so that I can save the bandwidth, and at the end, when there is questions, I'll switch it back on. All right. So the title of the talk by itself is design patterns, right? So the way I like to think about a lot of things in machine learning operations is there are good ways of doing things that we carry over from distributed systems, and some things like naturally work and some things don't work, right? So I'm going to talk about I'm going to structure this presentation from that perspective, and mostly refer to things as like design patterns and anti-patterns around what we think logically something should do for us, but in what scenarios it doesn't work that way. So what is MLOps, right? So MLOps is an intersection of development, operations, experimentation, and application delivery. So the biggest difference in my mind is the experimentation part around how quickly and how much we have to iterate our ML models, and how you need to apply it to different domains. That kind of complicates things a little bit in terms of how do you structure the pipeline. And also different applications in machine learning end up requiring different kinds of deployment support, especially when you're doing real world machine learning like IoT, edge IoT, or anything that where you're deploying your models in a real world and not as just a software system. Like the application delivery also changes quite a bit. So in that small intersection is is where a lot of evil things happen, and that is essentially what MLOps, at least on in my perspective. So the biggest difference though is that ML is code plus data, right? Which means that it embraces the challenges of both on the software engineering side and also on the data side. Software engineering challenges can be slow releases. You have your release trains that are not completely automated. Your pipelines could have a lot of variance. You might have a tight dependency between different repositories. You might have a very weirdly orchestrated build that works in a particular sequence. And if you change anything and you start introducing your ML models, things won't work. It'll just break. It's really brittle, right? Similarly, on the data side, one thing that's common is data inconsistencies. Meaning data is either inaccurate, it's incomplete. It can be any of that spectrum, but the inconsistencies in data is predominant, particularly for us while we were dealing with IoT data from factories. The sensors could be faulty. They would stop recording. So you would kind of start having to deal with a slew of these problems. Another thing is dynamic environments. Again, it goes back to my previous point. The factory environments in nature tend to be very dynamic, meaning that things change. There can be mechanical degradation. There can be a human operator who uses their domain knowledge to make some changes. So the environment by itself is going to be very different for the ML model, and it gets very unpredictable. And the skew is a big thing, where what you observe in training versus what you observe in production might be very different. And I'll talk about some of these things later in the slide. But now the challenge is you're building a pipeline where all these challenges come together in a very tightly coupled way, and that makes industrial AI in general incredibly hard to do. I mean, like, this is a fun use case, except that it made us rip our hair apart when we were doing it. Um, the biggest challenges here is that everything, like, that we saw in software development and everything we saw in data, like, just intersect in this domain, and that makes some of the learnings very interesting. So at a high level, what we did was we had we there in a factory there are process control systems. What these process control systems do is they either through expert control, through some other, like, a simple controller, right? They control the equipment operations in a factory, and that data is gathered through sensors. There are a lot of vendors, so you just essentially get all these IoT sensors streaming information. They get streamed to their dashboards internally, and they try to look at the performance of, like, a particular equipment, how is it doing under a particular condition and whatnot. And from there, like, and it is all behind the IT systems, like on firewalls that are like, that are put by those enterprises. So what makes it challenging is that now you need to pull the data out, which means there's a lot of heavy IT involvement. So what we ended up doing was we had our own transport layer where we built connectors which could interface with the process control systems inside a plant, and from there, like, it would go to our SaaS platform and we would inference that data, and we would inference the like, we would inference based on the data we are seeing, and we would send the results back through the same transport layer. So within, if you look at how the world looked inside Petuum, again, like, there were two paths. We had a batch and streaming. Batch is more where when we initially engage with our customers, when we get this data dump of everything that went on in that factory, so that we can learn historically what happened with that particular equipment, what are some of the corner cases that we could see in the data. But let me tell you this, the data is very biased, meaning that a lot of times you do not get all the information from the data, because the job of a plant operator is to keep everything running in pristine condition, which means that the data that you extract from a factory equipment might be a proper operating data where nothing ever bad happens, but at least it gives you a functional overview of, like, what could be the boundaries of safe zones. All these things become important in a safe, like, ML deployment in a real world. And then it would hit us. We started with Kafka, then we went with Pulsar, but it doesn't really matter what you use there. It hits the your message bus, and then we had a bunch of Spark jobs that would take the data, dump it in S3, which became our data lake. From there, like, we would analyze the data, build models, whatever it is, right? And we also had a direct path from Kafka directly to our streaming pipeline, where it would just hit the inferencer. And the intent there is that the models that you've already, like, the models we have already designed, and the features that we have already built, we can just leverage it without having to retrain. So, before we dig deeper, right, this is a standard thing that industry talks about around ML pipelines and how mature they are. You have the initial stage is obviously a manual deploy, right, where everything becomes manual. You're heavily relying on scripts, particular specific kinds of orchestration. Things, like, things will work. It'll you exactly know you have the right engineer to do the right thing, and all these things will be okay. The goals there are, it is okay to as a beginning. It's where everybody starts before they figure out what pieces need to be automated, and it is easy to get started, right? You can just, like, come up with your model on a Jupyter notebook, then have a bunch of scripts, just deploy it, to containerize it and deploy it, and everything might work okay. Challenge is that when your model is going to change, you have to go and redo the process again. So it's a lot of challenges when things are not going to be static, right? Then that takes you to the second part of the journey, where you start automating parts of the pipeline. You think about what your continuous training should be, your delivery should be. You optimize here on the deployment time. It tends to be less error prone because you are still not automating everything, but you're automating the pieces that where you think you will have more bang for the buck. The biggest challenge again in this stage is that it is still will not favor experimentation. You have a different flow for experimentation that's outside your build flow. But again, it gives you a little bit more stability, right? The North Star for everyone is to have a full CI/CD, and I mean we were not there. We were getting there, but again here you have several things, right? You have your full CI pipeline. It can be it can have multiple deploys every day. You have triggers to build the pipeline on demand. For instance, when you find a model performance deteriorating in the field, you can quickly use it as a trigger to redeploy something. You can continuously deploy your models, and your monitoring is very heavy. So at Petuum, what we did was we did parts of these things, though we didn't get everything. But we got to the triggers part, we got to monitoring, we got to certain things that helped us scale better. So the initial pipeline, again, it's a very simple thing. You have your S3, and you get you have a bunch of scripts that that run in a sequence. Then you have your collection of models. You store it in a model database, and you serve it, and you have your inferencing service that runs on top of it. So this is how everybody starts in my mind. When we had one customer we started our journey with, and it gave us flexibility to understand what the real needs there are in the domain, right? So we didn't focus more on the pipeline side, which turned out to be a problem later. But everything, it was painful because because we were in industrial IoT space, the environments being super dynamic, and the models had to go through multiple iterations, which added to the deployment time for us. So the first thing is that this turned out to be an anti-pattern, where we said that we are going to favor quick shipping and put things together, and repeatability is something we can look at it later. It turned out to be an anti-pattern for us because we missed that fact that we needed to that insight that we needed to allow rapid iteration, and we wanted to deploy multiple models a day. When we talked to the customers, when we had the second customer and they had a little bit different use case, we wanted to deploy 3 models together, 4 models together, A/B test stuff. We realized that we were we had to build all that stuff. So I feel it is very important to, in the initial stages, to think about configuration, testing pipelines, and validation at the minimum. When we looked at what we ended up doing, our deployment time was not that much compared to the configuration time we were spending, and also the validation time. So that takes the second lesson, that you don't need to replicate real world in your pipeline all the time. What I mean by this is, at least in industrial IoT models, what happens is you end up running your models for a certain duration of time, like multiple days, and then that's when you start identifying few environmental issues. You might have a slow buildup of something happening in the plant, and that will only show up after time, right? And you cannot always capture this in simulation. But one thing we did initially was we would run our validation loops for 3 days so our QA process was very long. We would finish our models, but we would run it for 3 to 4 days to have some comfort that the model is well tested. The challenge is that it is really a bad way, and we learned this thing later, that it's not the best approach, because you can always build uncertainty in the model, and your models as long as you optimize your pipeline where your models can train really fast in the real world, in real time, and there is an uncertainty that it models after the environment that it is operating in, you can get by without having these extensive validation loops. And that we learned, like, when we hit our third customer. But that is something that was pretty useful too. So this, for us, the stage 2 ML pipeline is, again, like, we had streams coming in from Pulsar, which it would hit the feature store and it would go to the inferencer on a streaming case. That's how we could inference very fast. But from a training perspective, we separated our experimentation, like I said, in a different world. We said that we're going to experiment outside. Whatever we do, then we have a integration to the source control repository, which is marked as SC in this diagram, and then that will launch the build pipeline, which would build the models and deploy it, right? But ideal world, that flow helped us to move faster, while also having time for our ML engineers to experiment and with different model architectures and different use cases, right? So that is something that helped us a lot. So the parts where we automated was on the way to generate the build pipelines. The triggers were still present, where we would say that if we had a heavy monitoring service plugged to the models that were running in the factories, and if the performance falls below a threshold, our build would trigger again, and we would deploy a new variant of the model to see what is going on. So the another thing we learned is that normally in machine learning there's this notion of training serving skew, where what you see in a training environment will be very different from a serving or a production environment, right? It happens because you might have inconsistent infrastructure, you might have variance in the system by itself. So what you thought your models would do would be something different. So, but in our case, while we tried to address that part, where we saw the skew happening was also because of the latency that was generated from the factory connection hub by itself. So, for an example is that there is this in a cement plant, there is a machine called a vertical mill, and the vertical mills are very sensitive equipments, meaning that when something goes out of control, you want to correct it in 5 seconds or so, and we could not, and every time our latency was about 15 to 20 seconds, and we tried to solve that problem by optimizing our infrastructure to no end, but it would still it brought us close. We got to 10 seconds, but that's the max we could do, because there was this real latency that our connection hub was was introducing. So one option, what we did was we installed an edge device in the customer data center, and for that one particular model, we would just we would deploy it there, right? Which means that the deployment was not as efficient as we had for the rest of our system, but that particular for that particular equipment, we would rely on latency and a much stable model than trying to figure out new things and learning on the field. So again, I feel it works based on different use cases you have, but that's the thing. So again, another thing that we noticed was, as we were very heavily invested in Spark, everything for us was Spark based, and it seeped into every aspect of our system. But Spark was not good for everything for us. For instance, Flink is very good at state management, and we started experimenting with it to understand if we can leverage Flink. But the challenges were that how easy it was to change our infrastructure, right? So we found out that it was a lot of cost that we didn't plan before. So we didn't structure our infra in a way that we could just onboard Flink very easily, right? So again, this becomes more of a platforming kind of pattern, where at what point do you if you have to, what is the cost of bringing a new technology on board? But within ML, as the landscape changes very fast, as technologies evolve, it is something that that's worthwhile to think about. The fifth one is that the real-time and batch streaming infra needs to be different, right? This is a normal expectation or normal understanding a lot of people have, because batch is lower operational requirement. You could run things based on historic data, do a lot of stuff. The problem is there's also, it introduces redundancy in the infrastructure. And the other thing is that a lot of batch work can also happen through streaming, which is much more efficient, because we, like, for instance, to accommodate with some of these queues and other stuff, we saw that we had to bump up our batch infra to, like, the training and entire training piece to have compatible production, like, infrastructure, like, similarities, right? Meaning that our high computes that we required in production because of streaming, because of the peak loads that we would see, we wanted to replicate it on batch to make sure that our models would still perform the same. But the challenge again there is, it was not needed. It was really a waste of resources, and we were introducing a lot of redundancy in it. As a startup, it was, when we looked at our AWS builds, it was crazy for us a few months. So there is a way to factor it in, push it back to Kafka, and then play everything as streaming. That also works. So again, it is not a proposal for which is better, but it is something that should be considered based on the requirements. The last anti-pattern is that ML is the hard part. This is what everybody thinks, and but the problem is ML is only a small part of operations. It's probably 10%. Everything else is about how do you deploy? Do you have any kind of life cycle management? Some things I've seen is that the packages tend to be self-contained, and a lot of entanglement between data and code. And like I said, there is complex orchestration that you run through with bunch of scripts, and again, not treating data as a code. So one thing we learned early was to have to treat data as a code, in the sense that version data, make sure that we audit the changes that happen, so we know who is making a change when, because the correlation between our data and the models that get out it's huge, right? So I mean, in summary, right, you do want to, there are 6 things. You want to think about repeatability, meaning that you are your infrastructure, the way you deploy models should be predictable and boring. Innovation need not happen there, but having that as a stable infrastructure is very helpful to learn about the real world and solve the real problems. Again, like I said, uncertainty is fine. Replicating real world is not what you should be doing, at least in the industrial IoT space. Rather, having your models, having room in your models to deal with the uncertainty, and modeling the uncertainty of the environment by itself is a much better design design approach than trying to understand everything and solve it in simulation and through pipelines. The latency monitoring is super important across the board, whether it is to address queue, to address the performance of the pipeline by itself. For us, that's been a life savior in many occasions, and that you can obviously piggyback alerting on top of it, and you can do the more hygienic stuff that what makes DevOps really fun. Then so from when you architect your pipelines, think about what happens if you're using Spark today, what happens if you're using Flink, what will happen if you use Beam, right? How does your data model change? What do you need to do to accommodate that shift? What would be the time to make this change in your pipeline? What would be the time to ship this feature or with this change, right? It's really important to think about it. In general, I like to think of 18 months from now where we will be as a business, both from a business perspective and also from a technology perspective. In 18 months, if the world changes and we have to do something radically different, are we going to start over? Are we going to incur a huge replatforming cost, right? So it's important to have that perspective. And again, this is again a common sense thing, but where you do want to avoid redundancy in infrastructure. purely because again it minimizes your points of the error that you can see. It also helps with cost significantly, at least for startups. I think it's a huge thing. So that's all I had. So I planned for 20 minutes with questions, so I think I finished on time. So anything you guys want to talk about, happy to talk about it. Cool. So yeah, what recommendation would you share to monitor latency? I mean, so it's more than a recommendation, right? You do want complete observable end-to-end observability in your pipeline. There are, which means that you measure everything that can be measured. So for instance, the way it worked for us was we would look at like what is the transit time, right? What happens to when we also track data lineage. We would also look at from a simple latency perspective on when the inferencer when we get a data from the sensor, what is the latency from what was recorded in the customer's system versus when we are getting it, right? So we measured a lot of things, and then we had a dashboard. We also used Prometheus extensively. It allowed us to aggregate our logs, create dashboards. So again, I don't think there's one pattern. It's based on whatever works for you, you do it. Tools, I think, are just a means to an end, but that's what I would say. Yeah, thanks, Imtiaz. And so how do you monitor and handle signal to noise ratio in sensors from industrial plants? This is a hard one because we don't know, right? The problem is when you do black box modeling in industrial IoT, everything becomes you assume that your data is okay, right? Your data captures everything that you want to know about that particular sensor. And that is the problem, though. That data is very biased because, like I said, an operator would be running that equipment in a perfect condition, which means that you would not see any kind of a failure condition in the data, and you would not even identify the signal to noise ratio. You can always look at the data sheets and say that this should be the ideal value, and this is is what the value is. And as long as it's a constant bias shift, it's okay, right? You can handle it. But what happens with sensors is that they mechanically degrade over time. So there is a distribution that you have to model. You really cannot take a fixed bias. But in general, ML models are very good at handling those things, as long as the bias in data by itself is addressed. If I know that my data is my data is real data that happened in a factory, that that I can rely on. I know everything, that when the sensor spiked, when it had an error value, when it was and I have feedback, and I can then construct a good model that might also be able to model the sensor behavior by itself. But it doesn't happen. So you kind of work with the plant operator back and forth to understand whether what we are doing is the right thing. So what we had was we would publish our model, and we had this phase of customer engagement where the final validation happened in the model, in the plant itself, where we would deploy the model, and we would work with our customer engagement engineers would work with the plant operators, monitoring every aspect of the model behavior, and we would response to a particular feed rate, what is happening, right? So I think it becomes back and forth, then we will iterate upon it. What did you use for tracking model information, Kubeflow? So yeah, so we had an internal platform. Actually, we didn't use Kubeflow or MLflow. But we went on this journey to be a platform company, and we started building a lot of the things in house. Today, I would not do that. I would because we started 3 years back as a company, and we were building a lot of these pieces, and we had internal tools that we used. Honestly speaking, Kubeflow or MLflow is amazing, right? You definitely can use things. The beauty of building an ML platform today is that purely using open source like a Kubeflow, MLbox, you can build this entire end-to-end platform very fast. In a week, you can get up and running, and that should be a very stable platform till you have to hit a growth stage. how did latency help with addressing the skew? So I'm defining skew in a very broad way. What I'm defining skew as is the difference that you see in production versus training, right? What happened in one of the use cases for us is that it caused a shift in windowing for the particular mill, because of our model, when we ran the tests, right, based on the data we were seeing, our models were performing as expected. But what was happening was that because of the latency, we were seeing a shift in the window, which meant that we were looking at data that was a bit late, right, or it's like stale. And that was the biggest problem, and we could not solve the window shift any other way. There is nothing we could do. So we went back to the customer data center and try to solve it on the edge. So the mentioned it better to leave uncertainties in the model instead of trying to explain everything. Could you? Yeah, absolutely. So for instance, right, there's a great paper from Google. So what Google does is they use this. They are very similar to what we were doing, and we took a lot of inspiration there. So Google uses machine learning models in the data centers to control actuators. And in a particular paper, I mean, I can find it out, but they talk about what kind of models work, what are some of the challenges there, right? And there's a nice analysis there where they talk about uncertainty modeling. So that's where we took a lot of inspiration from, and we try to apply to our domain. And what it eventually means is you want to model the environment as such, right? You want to understand how, looking at whatever I'm looking at in the environment today, and whatever I'm predicting, how much confidence do I have in my own predictions, right? And that is the uncertainty factor that you will have. So you ideally, what you're trying to do is you're trying to minimize the uncertainty that you have in the environment by learning more, right? Which means that you're essentially operating, as the more you operate in the environment, the more you learn about your predictions in response to what it is the right thing. So for that, one thing that helped us a lot is the feedback from a plant operator. So we never tried to replace human operators, but we had this as a tool that our human operators could use, which meant that there was a human in loop process that helped us with some of the validation cases where they would tell us that this is not a good number, and they would readjust it based whatever the ML model was doing, right? So that was a feedback for us that went into modeling our own uncertainty numbers, right? So that would be a concrete example. Great. Did I answer everybody's question? If I did not, please just holler and I'll go back to that. So I think it's not about tool by itself. Like I said, Spark was in the nuts and bolts of everything we did, and that also, Spark is amazing, and I've used Spark for several years now. But in some cases, it's just pain to do things with Spark. And so one thing is, for us at least, state management. Now Spark is getting there, but state management, Flink is, I think, much better. And that's not a simple swap change, right? That's not, you cannot just take away Spark in your system and bring Flink. Everything changes there. That we need to figure out the data models and a lot of the assumptions that we made about how we were moving data. There was so it was really hard. So it was a big platform project that we had to do. So we worked around it. Actually, we didn't even. I mean, when I left, we didn't finish it. Awesome. Yeah, thank you so much. It was really fun, and thank you for being a great audience. Absolutely. And if you have, by the way, if you have any questions, yeah, connect with me on LinkedIn. It's my first name. That's my ID. And happy to have any conversations there, and definitely would love to chat more. Yep. Thank you so much. Bye.